Okay, guys, so the next section of the USPNF is going to tackle 741, which is something that we called melting range. Now, yet again, just like with some of the other lectures that we've been talking about, melting range is something that's not quite necessarily new to us. So, melting range, if you've taken our CTC 114 course, is all about our melting point. So, how do we obtain a melting point? What is allowed to be used in melting point analysis? What are some of the settings that we will go through to determine the melting point according to the USP rules and regulations? So 741, if you've taken 114 before, is not a new topic, but everything surrounding that melting range could be a new topic, just addressed in a slightly different way, with maybe some particulars that we need to pay attention to if we are working in this type of regulated environment. So the first thing that you need to understand is that melting range is just that. So when we talk about melting range, we are talking about this concept that we know that things don't necessarily have melting points, right? There is no melting point that's going to be out there at all. Things are going to start at a certain temperature and things are going to end at a certain temperature. Now, those two start and end temperatures, they can be really, really close together, and we hope that they are close together. We do not want a wide range at all. Actually, the closer those values are, the better our stuff is going to be as far as purity goes. So that's what we have to go into this just knowing, is that most of the time when we do these types of tests and when we report this type of data, we are going to be reporting melting ranges. That's actually going to be the more appropriate type of way to tackle this type of test in a laboratory environment. So the temperature at which it begins to melt, that is something called the onset temperature. That is when we are beginning to see some crystals turn into a liquid. We begin to see a little bit of movement that's on the inside, and then sooner or later that's eventually going to turn into a liquid. The end temperature, that's really the temperature where everything is going to be a liquid at this point. There's no solid remnant behind at all. And that's something that we term as the clear temperature. And I want you to think of this as clear, and a lot of times these things melt into a liquid, and that liquid is going to be clear for the most part, and you can see through it. And the instrument actually sees this clear solution, and it can see through it as well. And I want you to think of that way to describe why we really use the word clear temperature to describe the ending melting point temperature that we will record. Next up, when we do talk about melting point, we are talking about melting temperature. These two things are really the same. So as we read through the monographs and as we see some of the testing, sometimes they'll refer to melting temperature, sometimes they'll refer to melting point, but either one of these are going to be okay to use. So just in case you really haven't had a very good general chemistry class, or maybe this is your first time talking about melting point and what is that, not a worry, we'll take just a couple of minutes here and we'll talk about what's going on in the melting process. So first off, we're going to have a solid material, and this is a solid state of mass. And in this solid state of mass, I want you to think of these as little tiny, itty bitty, little bitty particles that are all sandwiched together like a bunch of sardines. I mean, if you open up a sardine can, they're all crammed into one space. This area is doing the same thing. It is cramming as many of these little solid particles that it can on the inside. And there's really no room to wiggle, right? That's the thing with a solid matter. So the area that's in between these particles that are making the substance up, there is very minimal area in between. So they are shoulder to shoulder, elbow to elbow, and they are stuck together like glue. That is what we term as a solid. So what can happen is that we can take a solid in a laboratory, we can take a solid from maybe a refrigerator or a freezer, it doesn't matter, an ice cube's the same way, right? So we can take this solid and we can begin a heating process. And that heat is going to be represented with a triangle most of the time. That's kind of our shorthanded version of showing heat energy. So I can put a little flame to this solid piece of material. And what happens is that that flame, hot. That's what these particles kind of do. And these particles will begin to separate a little bit. So because they are separating slightly, we are seeing a little bit more wiggle room in between these particles that made the solid up. So because there's more room to wiggle, because there's more space in between their shoulders and their elbows, they begin to flow more freely on top of each other. So this extra space, this is going to create our nice flowy liquid that we are going to be measuring in the melting point analysis. So we are taking a solid, we're going to be heating it up, and the heat is going to create this extra little space in between these particles, and that extra space allows these free-flowing, or at least more free-flowing particles now, to venture off and go out in the yard and play, or go in the backyard and play, or roll over top of each other and go into the neighbor's yard. Doesn't matter as long as you get them out of your house. That's really all that matters. So that is the process of melting. That's what we call this. So with that said, what really is happening here at the chemical level? Well, we look at these intermolecular forces. That is what we are looking for with melting point systems and melting point analysis. So there's got to be some glue in a way that holds these particles together. Now, when I say glue, of course, I'm not talking about Elmer's glue or cement glue or any of the other sticky stuff, but there are attractions between these molecules that make them really hang out nice and close together. And that's what these intermolecular forces are. So there are many types of intermolecular forces, right? And one of these intermolecular forces could be just some hydrogen bonding. It's just one of the many that is out there, and that hydrogen bonding can happen, and the hydrogen bonding is this, quote, glue that holds these particles together and makes them kind of nestle with each other, and they get along and they don't really get angry, and they're just naturally in a solid form. So what happens in the heating process is that these intermolecular forces, well, we're putting some energy in them, and we're putting some friction between them, and we're spreading a lot of gossip, and we're talking about their boyfriends and the girlfriends, and the flame is just kind of kindling that anger and kindling that fire, and these molecules begin to hate each other. So they start to argue, and they start to bicker, and I'll just sit back and go, I'll do it again later. All right, so that's what the heat is for. And when we heat these solid particles up, we are destroying these intermolecular forces that are holding these molecules together. Hydrogen bonding is just one of many, yet again, right? So as these intermolecular forces are destroyed, then we start to chop all of those up, and the liquid particles now are beginning to form. In other words, what happens is that what was a bond maybe here between these two molecules now has been severed, and that kind of severance. Yeah, great show, by the way. If you've not watched it, please watch Severance. It's wonderful. So if you have not severed these two molecules, they're sticking together. They're going to be closer to each other, and that heat is going to destroy and rip those particles apart from each other. So this is how I want you to think of melting point. This is what melting point analysis is going to be doing, and it's what our instruments are going to be doing as well if we allow instrumentation to take over. So typically there's going to be some heat involved. Typically we're going to be looking at these solid pieces that are going to go to a liquid, and visually we can see that happening with our own eyeballs. All right. A couple of terms here that I want to talk about as we begin to venture down this road of more proper USPNF definitions of melting ranges and melting points. So there is something that is going to be called decomposition. And we do not want to be measuring decomposition temperatures, right? So when you look at decomposition, you are looking at the word decompose. Why on earth did I leave out so many letters? It's just one of those nights. It's one of those evenings. So decompose. And decompose basically means breaks down. So what happens here is that I could have a molecule, right? And we want to determine the melting point of this molecule, this solid substance that's been brought to us. There's a lot of molecules that are really close together. They're forming a solid state of matter, and we begin to rip those bonds apart, or intermolecular forces apart. So in the decomposition, what begins to happen here is that the molecule begins to heat up, right? Just like normal, like we would do a melting point, whatever, nothing fancy. We just begin to heat it up. And there could be at a certain point a decomposition temperature. And the decomposition temperature just means it just completely breaks in half. That's what this thing is all about. So it decomposes, it breaks up. And if it breaks up, this is no longer the molecule that we had before. It is like totally different stuff now, right? In other words, let's kind of think of this something, even though it doesn't do this necessarily, but let's take something like water, H2O. So if I heat, and let's say that this does decompose. If I heat this, well, if I heat it and the intermolecular forces are the only thing that's getting ripped apart, we're still going to end up with HOH, or the water molecule, at the end of this. That is a proper melting point. So in other words, I can take solid water, which is going to be ice, and I can heat that up, and I'm destroying intermolecular forces that are on the inside. And as I heat it up, and as those forces are getting destroyed, we start to have a looser network of water molecules, and I get a liquid form. So this would be something like water that you would be drinking because you're healthy, and you want to take a look at all of your moisture inside of your body and make sure that you don't get dehydrated. But suckle an ice cube, it'll kind of do the same thing. It's just melting inside of your mouth, and you're breaking those intermolecular bonds with your mouth. Who would have thought? Okay, so what happens in decomposition, though, is that if something decomposed, I would have a water molecule, and that water molecule would be solid, and there's intermolecular forces that are there. And as we begin to heat, those intermolecular forces begin to break down, just like normal. So I start to see some movement. I start to see maybe a liquid form. But at the same time, what could happen here is chop, chop. We could actually chop this molecule in some form or fashion in halves or multiple pieces, right? That's what decomposition is. It is a breakdown. So no longer would it be maybe water, but now it is maybe something totally different. I don't know. That's just kind of the thing, right? It decomposes. I'm just using water as an example. Even though it's a silly example, it'll get the point across, and that's what decomposition is all about. So if decomposition happens, you are breaking down the substance that you originally had. What this means is that there's a couple of things that will happen here as you do the melting point analysis. If decomposition happens, it is not uncommon for the substance to darken in color, for the substance to char, or for you to see bubbles that are getting formed in the decomposition of that solid material going into a liquid. So again, the idea here is you are ending up with something totally different than what you started with. So the idea here is that really a melting point, or is that a decomposition point? So for some issues, in some cases, you might see a D that is listed along with the temperature that they tell you is the target. And if you see a D, that probably means decomposition, and they're letting you know that you are really reporting here a decomposition temperature, not a melting point temperature. That could be a thing, right? It decomposes as you're heating it before you get to that proper temperature as far as a readout goes. All right, so if decomposition takes place, then what happens is that you are going to record the temperature at the very beginning of that process. When you start to see those changes take place, when you start to see it darken or char or bubble or maybe go into a liquid form, as soon as you see any of those observations that take place, you are undergoing the process of decomposition maybe. And the proper definition of a decomposition for the USPNF is we are going to record the beginning temperature of when this magic begins to happen. All right. So that's one of the things that we're going to take away from this discussion. Next up, let's go back to the actual proper melting point. And there is a term that we like to use. So if there is no decomposition at all, so this substance does not break down into something different, this substance stays that substance, does not get ripped apart, does not make anything new, it's just simply getting heated and the particles are beginning to hate each other, and there's just a little bit more room now between them. That's all that's going on, just more room, that's it. I wish they would be like that in Brunswick County. Make more room in between the houses, in the subdivisions. They'll get along. We need liquid environments over here, folks, and in Wilmington for sure. All right, so no decomposition. We say that the substance melts congruently. That's what that represents. All right. So if there's no composition, the substance melts congruently. In other words, melts normal. And what happens here is that if we record a temperature, we always record the end temperature of which that process takes place. The end temperature is always recorded. Now, proper lab technique is going to tell you to record the beginning melting and the proper end melting to give you an idea of how pure the substance might be. But by definition, the USPNF states that decomposition needs to be recorded as soon as it begins, and that a melting point needs to be recorded at the end of that particular type of process. No matter what goes on in a laboratory environment, I want you to understand that this process takes a little bit of time, right? So it's not going to be immediate. As we heat this solid, as we put more energy into it, as we rip those intermolecular forces, one from another, that process begins to take up a little bit of time. So what we state here is that there is thermal lag in our melting point analysis process. That means it takes a little bit of time for the thermometer to catch up with what is happening on the inside of that solid being changed over to a liquid. So thermal lag exists with everything. Therefore, it is important to go very slow with this process. So the question is, hey, Tracy, how slow is slow enough? Well, believe it or not, this USPNF definition is going to tell you 1 degree per every minute. Oh my God, I'm going to be here forever in order to do a test. Why? That's just how it gets, folks. So this is why instrumentation is very important. It allows me to automate this process. It allows me to let this thing do its thing. I'll go off, I'll do something different. I'll come back after that instrument is now finished, and it makes my life much easier. But we have to go extremely slow in order to get a proper melting point. And the reason is because the process does take time to convert, and I don't want to heat this up so fast that the temperature is outpacing what is going on at the chemical level. So 1 degree Celsius per minute is what they're going to be after with our melting point apparatuses. Next up, you need to understand that the USPNF does allow us a little bit of flexibility on how we do the melting point. They call it apparatus number 1 and apparatus number 2. Apparatus number 1 is with a hand measurement. So this is like old school, get me out some glassware, some mineral oil, let me kind of do my thing. And apparatus number 2 is more automation, it's more instrumentation. That will take over. I don't have to worry with it. I've got more flexibility and freedom. And maybe I'm going to get better sets of data as well because there's more control. Both versions are approved at the USPNF. Both versions, though, also will include USP reference standards. Go figure! They want me to spend hundreds of dollars on a standard in order to kind of double check my process and my reporting and my laboratory technique. So I'm going to take a look at some of these reference standards that we would be using. Whether we do hand measurement or instrument measurement, it doesn't really matter, but the reference standards are going to have to be used in some form or in some fashion. All right, so if I take a look at some of these USP reference standards, what do they look like, right? Well, here's just a very quick list of a search in the USP standard database. And they would prefer you to use USP standards, of course. You don't have to order them from USP. You can order them from any supplier that carries USP labeled products. But all of these are USP labeled. Wherever you get them, it doesn't matter. If you order them strictly from the USPNF, folks, the costs here are all about the same type of ballpark. We are looking at about $200 for 1 gram of material. Whoa, my God. Talk about budget, talk about money. 1 gram of material is more than enough to do multiple tests, right? That is not an issue. But I'm talking about 1 gram. Do you know that if I ordered something like caffeine, I could probably get a non-USP version of caffeine, and I could order it with very high purity for various things that we do in the lab, and I could probably order 100 grams of this stuff or 250 grams of this stuff for $50 to $100, depending on the supplier. I mean, that compared to 1 gram for $200, just because it has the USP label, just because it's very high purity types of products, this is where the money gimmick starts to come into place, right? So no matter what you choose, you're looking about a $200 investment. It will last a few different melting point attempts. 1 gram will do more than 1 test. That's not a problem, but you will go through it fairly quickly. If you take a look at the listing that I pulled from, it varies a little bit. So if we go up and take a look at acid analyte, we're looking at a 114 degree melting point. And then here is caffeine, and caffeine is 236 for its melting point. And then if I go to phenyl salicylate, this is 41 degrees for its melting point. And I hope that you are getting a sense of why these things are included in the list. Because what's happening here is that if I have a sample that has been submitted to the lab, and let's say that I know what the melting point should be, right? Let's say that my melting point should be about 80 degrees Celsius. Okay, not a big deal. I'm going to take my sample, I'm going to walk it into the lab, I'm going to do hand measurement, or I'm going to do instrument measurement, and that particular sample I think should be melting at about 80 degrees. I put it on the machine, I put it on the glassware, I record my data, and I get like 82 or 83. Okay, well, we're close, and we're in the ballpark, but that's not the only thing that I can do or that I should be doing in a laboratory. So what happens here with USPNF is that they want you to test that process with a USP standard. So what would happen here is that I would take this really high purity standard, and I would also go through the process of doing a melting point determination with that as well. And I would do these kind of at the same time. I would do one and then do the other, or maybe do both at the same time if the instrumentation and stuff allows it. Why not, right? But they're giving you choices that you're seeing on the screen so that way you can play match game. So if I get something that has an expected melting point of 80 degrees, then why on earth am I going to choose potassium nitrate to go with? That has a melting point of 334. Does that even make any sense? I don't think it does. So I probably would not choose that in order to run along with my sample that is supposed to be melting at 80. So what would happen is that I would go, oh, look, here's vanillin. Vanillin has a melting point of like 81. So that's really close to what my suspected samples are going to be melting at. And I would want these to play the same game. I would want them to be pretty close as possible. They don't have to be an exact match. But if I'm given a list of choices, I'm probably going to pick this one because that's the closest to one of the samples that I'm going to be bringing in and testing in a lab. So I'm going to go through the process of testing the USP version of vanillin to make sure that I can get something that is close to 81. And then I'm going to go through the process of testing my samples. If I did the vanillin the proper way and I get really good data, I'm probably going to do my samples the same way, and I'm going to get really good data with that as well. If I have an instrument that can allow vanillin to go in as well as samples to go in, then I'm going to take advantage of that. I'm going to put both of them in at the same time. I'm going to start the melting point process. I'm going to walk away and let the machine take over. And then I'm going to come back. I'll take a look at the vanillin temperature that my machine gives me, and then I'll take a look at my sample temperatures that my machine gives me. If my vanillin is really close to expected values, then my samples are going to be really close to my expected values as well. If you've done 114, you did a little bit of the hand way of doing melting point analysis. So this is something that we call a fill tube. A fill tube is going to be filled with, most of the time, something like mineral oil or some type of oil that can hold pretty hot heat. If you go through and take a look at some of the listings, I mean, we're like 165, 271, 236, 334. We've got to be able to do something other than water to fill the fill tube. And the reason is because water has a melting point or a boiling point of 100. Sorry, a boiling point of 100. So if water is in that fill tube and I'm heating it up, I'm only going to get to 100 degrees, and that's going to be about it. Anything over 100 degrees, folks, it's not going to melt for you. So I need to choose some type of oil. That way I can get really hot temperatures out of the fill tube, and I can get those melting points that are way over 100, because if not, I'm just going to boil the water off, and that's the only thing that I'm going to accomplish in the fill tube method. So hot oil, that's actually you better take a look, because we are going to be heating up this piece of glassware, and this piece of glassware is going to be filled with really hot oil, and if that piece of glassware cracks or shatters or breaks, all of that hot oil is going to go everywhere. And I hope it doesn't go on your unprotected face because you were not wearing safety glasses at the time. Shame on you. You should never do that. So heating up glassware, always put safety first. Put on your safety glasses, and you will be a much happier camper if something does explode. As far as the fill tube goes, a lot of times what we're doing is heating this area right in here. And the reason is because if we only put the flame here and that is it, then we're going to create a hot spot, and we do not want a hot spot created. A hot spot would be maybe the possibility of a certain area of the oil is going to be way hotter than the maybe top layer of the oil. That's what we want to prevent, and the field tube allows circulation here. So as I heat the bottom elbow and as I heat the bottom of the field tube, I just kind of swish that flame back and forth, back and forth, back and forth. This is going to create a nice little current here. So hot oil will kind of go up, and hot oil will go around the bend, and hot oil will make its way to the top, and we begin some circulation that happens in the field tube. That is why it's made the way that it's made. So this gives me even heating. This makes sure that the temperature that I'm recording is actually the proper temperature that the thermometer is supplying and that the oil is supplying as well. What you're seeing here over on the right hand side is just a close-up. So if you take a look at your field tube, right there it is, and that field tube looks like it's going to have a thermometer that's going to be dipped in it, as well as a capillary tube that has your sample. So here is the thermometer, and that thermometer goes into the field tube inside of the hot oil. And then we have a tiny capillary, and that tiny capillary is over here to the side. We have attached that to a thermometer, sometimes just using a rubber band or a piece of, elastic, something that's going to secure it in place. And we got a nice little plug of solid material down here at the very bottom. So make sure you choose capillary tubes that have a sealed end on them, because if you don't, the solid's just going to fall through. It doesn't make any sense. So again, things that I have to say, and that's one of them. This capillary tube is going to be attached to the thermometer. Notice they're about the same level as far as, even with the thermometer and the capillary tube, and they are also even with the elbow or the side arm of the field tube. So in the picture to the left, I'm going to put a thermometer, and I want my thermometer being right here because that is right there at the elbow. So you want to make sure that the oil covers the thermometer bulb. You want to make sure that the oil covers your solid material in the capillary tube, and you want to make sure that the oil at least goes above this side arm, so that way your oil can circulate the proper way. So that is what we call a field tube, and we probably will not be focused on field tubes for 115, but instead we're going to be focused on the melting point system. So these are instrumentation pieces that are USP approved, and we can go through and use these, no hot oil required, and we can pack some of our capillaries, put these inside of our melting point systems, and begin some readouts of what my melting points are going to be. So that's where this lecture video is going to stop. In the next video, we're going to be talking about different ways to do these melting points, both by hand and by instrument, because there are certain directions inside of the USP that we need to focus on. As far as the USP, 731 is what we are referring to. I'm sorry, 741 is what we are referring to. And 741 is stated melting range or melting temperature. So in this process and in this test, we want to go through and we want to make sure that we fully understand what these rules and regulations are going to be if I do this proper procedure in a regulated laboratory. So you probably have a copy of this at some point. It's about 3 pages, but 741 is what we're focused on now. And there's a little blurb of background information. That's what I'm giving to you now. And then the apparatus section is going to follow that. And the apparatus section is going to be broken down into 2 major players. And then within those major players, we have what we call Class 1 and Class 2 and Class 3. So we'll talk about the minor differences between all of these. But if you want a reference document, it's right here. So bring out your copy, scribble some notes on it, because this is going to be our focus in the next video for sure.